Okay, in this segment, I want to discuss how natural selection can be seen as a substitution process. We'll use our case of the evolving insects. Here we have our chubby stick insect here in this generation, and the population is evolving thinner bodies over here on the right. And we've already drawn this process, but in this diagram I want to emphasize the idea of a substitution process. So here we have the 25%er giving rise to the next generation. There's some variation in the body shapes of that generation. Most of the individuals are like the parent, 25%ers. Some are a little thinner, a 40%er. Some are a little chubbier, 15%er. Now, in an environment filled with sticks and predators, the thinner bodies will have an advantage. The camouflage of the 40%er is a little bit better than the 25 and much more better than the 15. And so the idea is birds will not eat the 40%ers as much as the 25 and 15%ers. This means the 40%ers are going to, on average, have more babies. And because they are the ones that are having more babies than the 25 and the 15%ers, we can think of them as substituting their offspring in the next generation for the offspring of these other individuals that would have been around had there been no predators in the environment. So that's the idea of the substitution, that it's the babies of the most fit individuals are substituting or being substituted for the babies of the less fit individuals. So the next generation has an overrepresentation of the babies from the most fit individuals and an underrepresentation of the babies from the less fit individuals. Okay, now we can graphically display this process. Take a look at this graph. Looks complicated, but on the left, the y-axis, you have number of individuals in the population. And on the x-axis, we have body shape. Fat, medium, thin. And then we have another dimension here of time. And so this graph is going to help us understand how populations evolve over time. In our case, the case of the stick insect. Now there are several curves here. The blue one, then a dashed red one, and then another blue one. This is the same population, but just over time. And I just made them blue and red just so we could see the curves a little bit more easily. So let's see what's happening over time. Initially, the population, we'll start over here on the left, is in the fat category. So most of the individuals, so the highest number here, most of the individuals were fat. However, the curve indicates that there are some individuals that are a little thinner than fat, and some individuals are a little fatter than fat. So we go over to the y-axis to see how many individuals are the fattest in the population, and it's a small number. Most of the individuals are of the average fatness for that generation. Some, very few, are thinner than fat. They're the thinnest of that generation. Now what this graph shows is that over time, the average body shape is changing over time. So whereas in past generations, the average body type was fat, over time, the average body type is getting medium and then on towards thin. And so this is the process of natural selection, that the population of insects is evolving. The thin body shape is evolving in this population. Now to see how that's happening, let's take a look at just one section of this graph. So now we see two generations, the original ancestral generation, where most individuals were fat, and then the next generation, the dotted red line. So when birds are in the environment, and again, remember, there are sticks in the environment, so your body shape is a measure of your camouflage. The thinnest individuals in each generation will have the advantage, and those individuals are represented by the right part of this curve. You see, so in the ancestral generation, in the first generation, the average individual is fat. but some individuals are thinner than that. These are the thinnest ones in that generation. It's those individuals that have the advantage when there are predators around. And so they will be more likely to survive and have babies. But look what happens when they have babies. That means that the average body shape in the next generation is going to be a little shifted to the right from the previous generation. You see, because it was these individuals that are a little to the right of the average body shape, fat, it's the thinner ones that are going to have babies. So that means the average of the next generation will be a little bit thinner. And likewise in this generation, in the red line there, that generation, it's going to be these individuals to the right of the average, the thinnest individuals of the generation are going to be having the most babies. And so for the next generation, the average will be a little bit thinner than the previous average. So in this way, then, over time, predators are going to be eating the average ones and the less and the fatter than average ones each generation more often than they will eat the thinnest members of every generation. Because the thinnest members of every generation are more likely to survive and reproduce, the average body shape in the next generation will be shifted to the right. And over time, the population will be evolving thinner and thinner bodies. And that's what we see here, starting with individuals, say, on average 25% stick-like body. Over time, the average is getting higher. So the average body shape has increased from, say, 25% to 40% in this generation. And it'll keep on going until individuals are just very well camouflaged in their environment, what we call the 100% stick insects.